Good morning, ladies and gentlemen. Our next portion of electricity will be to talk about electrical power. Now, whenever we talk about electrical power and electrical energy, the reason it's ultimately so useful is because it could be turned into other types of power or types of energy. And because it can be turned into other types of energy, including mechanical energy, we can always go back to our original formula for mechanical power, which is power is equal to work over time. And the unit we're going to use for electrical power, or for electrical energy also, is going to be joules per second, or watts. Okay? So we are going to deal with our original formula. And here we can see mechanical energy actually being turned into electrical energy. But what's more interesting enough is when he connects it to a second generator. Now watch. The mechanical energy is turning into electrical energy, which is turning back into mechanical energy. But notice, does the second generator rotate at the same rate as the original? No, it doesn't. I mean, even if we talk about electrical energy being turned into mechanical energy, for example, here, in this simple example, we have mechanical energy being done. The work is equal to mgh. So therefore, there's going to be a certain amount of power being applied if you divide it by the time that it takes for this entire lifting. Okay? But that power ultimately came from sort of electrical energy, electrical power. And to solve for how much electrical power there is, and to solve for ultimately that efficiency, here's our formula. Power, electrical power, is simply equal to the potential difference times the current. So you could say it's volts times amps. Of course, the unit that we use is going to be watts. However, if you think about our formula that we spoke about in a couple of videos ago about potential difference equals to I times R, if you were to substitute the V with the IR, you could rewrite the formula. Therefore, power could also equal to IR times I, or in other words, I squared R, if you want to manipulate it. You can even manipulate it to replace I, so therefore power would also equal to V squared over R. Any of these formulas are technically true. They are all derived from the same formula of power equals VI, and that's the most common formula that we're going to use ourselves. Okay? Keep in mind that this can always be set back equal to our original formula for power, work over time. So the work would actually be the electrical energy used. Okay? Now we do a quick practice question. A lamp draws a current of 0.5 amps when connected to a 120 volt source. So I is equal to 0.5 amps. V is equal to 120 volts. They ask what is the resistance of the lamp. That's our original formula. R is simply equal to V over I. So it equals to 120 volts over 0.5 amps, which equals to 240 ohms. When they ask us to solve for power instead, power is equal to VI, So that equals to 120 volts times 0.5 amps, which is equal to 60 watts. And if I want to solve for how much energy was used up, assuming that it's left on for 1 hour, time of 1 hour is the same as 3,600 seconds. Okay. Work is simply equal to power times time, so equals to 60 watts times 3,600 seconds, which is equal to 216,000 joules. Okay, so in terms of energy, we can see that it uses up 216,000 joules of energy per hour. However, a light bulb is not very efficient. In fact, 90% of the energy of the light bulb turns into heat. Only 10% of the energy is being used for light. So if I were to actually ask you, how do you calculate the efficiency of the light bulb, or how efficient is that light bulb? Knowing the efficiency, we can calculate that the power used for actually light is equal to 0.1 times the power that we have found times the 60 watts, which would only equal to 6 watts being used for light. Or the energy being used for light would have been 0.1 times 216,000 joules. Okay, so it's very, very inefficient. We could do another practice problem over here. It says calculate the resistance of a 40-watt automobile light designed for 12 volts. In this case over here, we know that the power is equal to 40 watts. The potential difference is 12 volts. They're asking us for the resistance, R. You could go about this one of two ways. You could solve for, well, knowing P and V, you can automatically solve for I using P is equal to VI. So I would equal to 40 watts divided by 12 volts, which would equal to 3.33 amps. And then knowing the current, you could then solve for the resistance. R is simply equal to V over I, which is then equal to 12 volts divided by 3.33 amps, which would be equal to 3.6 ohms. Okay, so that's just using our two separate formulas that we've learned for this unit so far. However, if you had chosen to combine the formulas together, you could have also done P is equal to V squared over R, 12 volts squared divided by 40 watts would equal to R, which would then again equal to 3.6 ohms. Okay, because we had flipped these two variables. This is more of an efficiency question here. We have the electric motor operating a pump that irrigates a farmer's crop. It pumps 10,000 liters of water. Now, if you recall from chemistry, 1 gram of water was equal to 1 milliliter. So therefore, 10,000 liters of water is the same thing as 10,000 kilograms. So this is actually the mass of the water that's being given. And it's pumped at vertical distance, a height of 8 meters, into a field each hour. So times 1 hour to 3,600 seconds. The motor has an operating resistance of 22 ohms. And it's connected across a 110 volt source. Okay. The first question they ask, how much current does the motor draw? Well, we can solve for both current and the power actually. I would be equal to V divided by R, which is equal to 110 volts divided by 22 ohms, which is equal to 5 amps. And the power, the electrical power, so I'll say the power of the motor, well, I'll say the electrical power, is equal to 110 volts times the current of 5 amps, so it's actually equal to 550 watts. Okay. Now, but when they ask us how efficient is this motor, well, we actually have to look back at our original efficiency formula from thermodynamics. In other words, the efficiency is equal to how much work per second was actually done. So this would be the physical work or mechanical work divided by QH over time. In this case, divided by the amount of energy that's put in. In this example, we put in electrical energy. So if I want to solve for the efficiency of this problem, I need to solve for the physical work using this information and divide that by my electrical power. So I need to solve for the physical power divided by the electrical power. So the physical power, I'm about to erase all this, is equal to power is equal to work over time, or mgh divided by t. That's the physical work done. So they raised 10,000 kilograms times 10 meters per second squared times the height of 8 meters divided by 3,600 seconds, and get a total work over time, a physical work over time, equal to 222.22 watts. So therefore, my efficiency would equal to the work over time done, so 222.22 watts, divided by the amount of energy I'm putting in per second, which is the electrical energy, 550 watts. I can find that my efficiency in this case is equal to 0.404. I know it seems like it was a long problem, but ultimately I just had to solve for the mechanical power and divide that by the electrical power to solve for the efficiency. Okay. And the last thing we're going to talk about today is the kilowatt hour. Now, the reason we're talking about the kilowatt hour is because if you go outside your home, there's an electric meter that says kilowatt hours. So I want you guys to understand, what does that actually mean? What does this unit measure? Well, kilowatt, of course, is a unit of power. Hour is a unit for time. Kilowatt hour is really just a unit of energy. So I know the word watt is in there, but it actually means energy. It's kilowatts times hour. So whenever you're doing any problem to solve for kilowatt hours, make sure you convert power into kilowatts and then convert time into hours. Okay, and you simply multiply the two. So if you take a look at question 8, they state that an electric heater is drawing 15 amps on a 120 volt line. in this case, power equals to V times I equals to 120 volts times 15 amps, which is equal to 1,800 watts. Now, because I want this in kilowatts, I'll divide this by 1,000 and end up with 1.8 kilowatts. Now, they ask us, how much does it cost per month if it operates 3 hours per day and the company charges 10.5 cents per kilowatt hour? Well, let's figure out the time first. The time, they say, is 3 hours per day for a month. We can assume that a month has 30 days, so therefore this is a total of 90 hours. Now that's the unit I actually want to use already. So to solve for the amount of work that's done, work is equal to power times time, equals to 1.8 kilowatts times 90 hours. So the total energy being used is equal to 162 kilowatt hours. And if I wanted to know how much my electrical bill is, if they're billing me at 10.5 cents per kilowatt hour, that's simply a conversion factor. So I do 162 kilowatt hours. 1 kilowatt hour is equal to $0.105. So in the end, I end up with $17.01. Okay, so that's how we solve for our energy bill.